All right, people, welcome back. So let's do another example of Stokes' theorem here. Maybe this time we'll go in the other direction. So let's start with the same circle from the last example, the circle of radius 2, centered at the origin of the xz plane in three-dimensional space. So now let's change the vector field on it. So now let's consider the vector field. Big F of xyz is minus y in the first component, x in the second component, and 0 in the last component. We know how this one should work now. So as a three-dimensional vector field, we have at every height z, we have a copy of the xy plane. And in each one of those copies of the xy plane, this vector field will act exactly like that one that we met first time, that is just flowing kind of in circles around the origin. So I think in the section about curl, we discussed that the curl of this vector field is a constant vector field that points everywhere in the positive z direction. Okay, and so now it seems like that vector field's pretty easy. So even though surface integrals aren't always the nicest thing, it might be like the load might be lightened a little bit here by having a nice vector field to take a surface integral of. So we are going to trade a line integral of f along c with a surface integral of this easier vector field curl of f along the same hemisphere s from the previous example. So let's assume everything has the same orientation as it did from that example. And so just a sort of reminder, here is that picture here of the surface S. And so we're going to need a parametrization of that surface S. And we can use spherical coordinates, right? Since it's just part of a sphere centered at the origin, that sphere had radius 2. So in spherical coordinates, it would be rho equals to 2. So now using the spherical coordinate transformation, we can write a parametrization for the surface. I'm going to write as little s here as being 2 sine of phi cosine of theta in the first component. So that's the x function there. The y function will be 2 sine of phi sine of theta, and the z function will be 2 cosine of phi. Now, the one thing here is that we have to mind is the bounds. So we'll still have top and bottom. So phi will still go from 0 to pi here, because we go all the way from the top part to the bottom part. But to get just this right hemisphere here, we're going to let theta vary from 0 along the positive x-axis to just to pi. Okay, I think this is maybe the first example we've seen where we have theta not going all the way around, right? So we're going to cut it off at just pi. All right. So now we're going to need the tangent vectors for that parametrization. So we'll take derivatives of the function little s with respect to theta and with respect to phi, and we get these vectors here. Now, we need to know the reason we're taking these tangent vectors to begin with is that we would like to find the normal vector by taking their cross product. Now, we already have a description of which direction that normal vector we want to be pointing in. We want it to be pointing in the positive y direction. So let's just evaluate these two tangent vectors at our favorite values of theta and phi. And so I'm going to go back here for a second and notice that on this picture, when theta is pi over 2 and phi is also pi over 2, we're right here at this point here where I've actually drawn one of these vectors n. And so we're looking at that single point. We would like to be finding the vector that goes just in the positive y direction. Okay, so we'll evaluate these tangent vectors at theta and phi both equal to pi over 2. And what we get is that s sub theta is minus 2 in the first component and 0 in the other two components. And s sub phi is 0 in the first two components and minus 2 in the last one. So that their cross product here will be minus 4 in the y component and 0 in the others, with that points in the negative y direction. And we wanted our vector to point in the positive y direction, so we'll take the cross product in the opposite order. And that will be the normal vector field that we will use across our surface S when we are forming our surface integral. So our vector field curl of f is constant. It is always this vector 0, 0, 2, so there's no need to have to compose it with the parametrization. This is always going to be what we get out at the end. But now we can compute for general values of theta and phi that cross product s sub phi cross s sub theta will be given to us as follows. It will be 4 sine squared phi cosine of theta in the first component. It will be 4 sine squared phi sine of theta in the second component. And it will be 4 cosine of phi sine of phi in the third component. So then we can take the dot product of curl of f with this vector field here, and the first two components become negligible because they're multiplied by 0, and so we'll just be left with 8 cosine phi sine phi. Great. So that is what we want to integrate over our bounds as phi goes from 0 to pi and as theta goes from 0 to pi. And so just looking here at the inside phi integral, you can see that this is going to be a u substitution, where u equals to sine of phi. But sine of 0, when you change the bounds, sine of 0 and sine of pi are both equal to 0. So that means that this inside integral can really be changed to an integral from 0 to 0 of, what, 8u du? But the integral from 0 to 0 of any function will be 0 itself, and then further integrating the 0 function with respect to theta doesn't give us anything. So ultimately, this whole surface integral of the curl of f along S is equal to 0. Okay, so by Stokes' theorem then, the original vector field, the one that swirled around the origins and all the xy planes, if we were to do the line integral of that guy along C, we'd get 0 as well, because Stokes' theorem says that this integral must equal to this one over here. Okay, and we can maybe even make sense of thinking about what line integrals compute, right? They compute some kind of work done by a vector field to move a particle along a certain curve. Well, notice that this curve C is everywhere perpendicular to these vectors from the vector field F. So it should make sense then that the vectors from F are really doing no work to move a particle along C. All right. So come back in the next video. I think we will do one more example of Stokes' theorem, and that'll be it for this. So we'll see you then.